Morning, Eagle Chemists. What we're going to do today is look at unusual properties of water. You can call this a demo or lab, whatever you want to call it. But what I'm going to do is give you some general information before we start. What you're looking at, this Mickey Mouse molecule that we're looking at, is a Bohr diagram of water. If you look in the center in the blue right here, that is oxygen. Oxygen has 8 protons, and that means 8 electrons, 2 in the first energy level, 6 in the second energy level. It wants to have 2 more electrons, and so if it comes close to hydrogen, hydrogen will share in 2 different places with electrons, and what happens is we end up getting a polar molecule. What that means is that there is an uneven distribution. These electrons down here are pushing the other electrons away, and so water has this bent shape, which we've talked about before. Mickey Mouse's chin here is negatively charged because there's 2 unshared pairs of electrons, and Mickey's ears are positively charged, and the attraction between molecules is going to occur between the negative charge of the oxygen coming close to the positive charge on hydrogen on another molecule, and that's what causes hydrogen bonding, which gives all the weird properties that water has. All right, there is a structural formula showing the same thing. Oxygen is slightly negative on one end, hydrogen slightly positive on the other end. If we look at a dot diagram, we can kind of see from this before, we've talked about this. Here's the electrons pulled close to oxygen. Oxygen is highly electronegative, and so it pulls the electrons away. Hydrogen's nothing but a proton electron, so this hydrogen represents a proton, which is positively charged. That's why the H's are the positive end of the molecule, and the negative end is where the oxygen is at, where those unshared pairs of electrons are at, right? And this is what makes water polar. Water's polar, all right? A polar molecule is one that has an uneven distribution of electrons. Like there's more electrons here than there are on the other side because they're pulled away from the hydrogens. That's what makes it polar. And there's an old saying called like dissolves like. Polar substances tend to dissolve in other polar substances. So if something dissolves in water, that means it's polar. If it won't mix with water, that means it's nonpolar. All right, this diagram right here is of liquid water. And according to the kinetic theory, all particles are moving all the time. Well, here we have 6 water molecules, and I show them being stationary in one place, but they're actually bouncing around. Now, there's some attraction between them, between the hydrogens and the oxygens, tending to get them to stick together like this. That's the hydrogen bonding. But if you cool them down and you slow them down, what will happen is water will form a crystal, and you guys have all seen a snowflake. Well, this is why it forms that snowflake side like this, because what happens is the water molecules will line up like you're seeing here, and what holds them in place is this hydrogen bond between the hydrogens and oxygen. The hydrogen of one molecule, oxygen of the other one, there's an attraction that holds them in place, and that's really pretty strong, right? But what's unique about this water, and water is the only substance I know that does this, it actually expands when it freezes. In other words, it takes up more space. It's going to become less dense when it expands, and it's because of this open crystalline structure that it has in the middle. There's an open space inside the snowflake. So if you've ever seen a snowflake, they really are 6-sided, and this is the reason why, because of the shape of this molecule. All right, in this lab or in this demo, what you're going is you're going from table to table, and you're going to look at different examples of these unusual properties of water. So what you're doing right now is you're looking at a beaker of water, and what I'm going to do is I'm going to add some ice cubes to it. And one of the unusual properties of water is that the water expands when it freezes. All right, so I want you to explain why that happens in here, and I want you to draw a picture of what you see. Where's the ice at in relationship to the water? And you need to know the chemical formulas for the water. Pause this if you need to. All right, in the next step, what you guys are going to do is you would try to float a needle in the water. All right, in water. So what I have here is I have and I don't know if you can see this, but there is water in here. This is a petri dish, a flat little dish, usually used for bacteria, but it works pretty well for this too. And I have a stainless steel needle over here. So I'm going to pick up the stainless steel needle. And if I just drop it in the water, okay, that time it floats. It floats in the surface tension on there, and it's stuck in there. And if I pull that thing out, for example, if I put it in at an angle, oh, that works okay. But if I put it in at an angle, a lot of times what will happen is it will just pierce the water
and that one is floating on top really, really well. So it's even hard for me to get that sink. But if I were to push it down and sink it like that, there it's staying on the bottom. But if I pick it up and I can get it to float just perfectly in that surface tension, whoops. I'm going to get it to float just on the surface there, like that. And so there, it's not sinking on the bottom. Probably easier to see in person than it is on the video. Let's see if we can't get something a little bigger to float in there. Here's a paper clip, and we're going to try to get this thing to float perfectly in there. And so the idea is to get this thing flat to the surface. And there's a paper clip floating. That one's a little more challenging, but I know that you guys can probably do that. All right, in the next step, what you guys are going to do is you're supposed to take a coffee cup, which you're looking at right now, and then overfill that thing if you can. So what I'm going to do, I'm going to move my camera just a little bit here, like this, and I'm going to pour water into this coffee cup. I don't know if you guys can see it, but the water is actually above the level of the brim of the thing. I'm going to put this down just a little bit. Maybe you can see that a little better. Or just a little bit more and see if we can get a little more in there. Okay, so now that's pretty good. It's above the level, and maybe it's worked better if we hit something. Black background behind it, but you can see the water just above the level of the cup. And gravity's trying to pull it over the edge, but something else is pulling it back. Let's see if we can't add just a little bit more water. That's about the max. It's about ready to go over the edge there. All right, but like I said, gravity's trying to pull it over the edge. Something's pulling back on it. All right, what you're looking at right now is a graduated cylinder with some water in it. I'm going to try to get this as close up and level as I can here. And we're going to put a black background behind it here in a second here so you can kind of see this. All right, I don't know how well you can see that, but the surface of that is curved. It's higher on the edges and it's lower in the middle. Maybe that's better. You can see it better that way against the white background. But it's curved. In other words, it's kind of got a curved shape like this. And so that's meniscus. That's something we're careful of. When we measure in a graduated cylinder, we always measure from the bottom because the water stays stuck in there. It's hard to get all the water out of graduated cylinder when you empty it. And so that amount of water that stays stuck to the sides like it is right now, gravity's pulling it down in the middle. Water is attracted to the sides of the graduated cylinder, and so when you pour it out, some of the water stays stuck in the graduated cylinder. All right, one of the things you can do to show how sticky or how cohesive water is to itself and to other things is we're going to try to see how many drops of water we can fit on a penny without it overflowing the edge. So we're going to try first the head side of the penny, so let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, and at 22 it went over the edge, so I got 21 drops of water to fit on that penny. Let's see if it's different on the tail side. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Oh, and this time it went 21 went over. So the first one I got 21 on the head side, I got 20 on the tail side. All right, what I have here is a beaker of water, and there's a glass stirring rod in it. And this is a bottle of oil. So I'm going to put the oil in it, and I want you to watch what happens when I put the oil in. The oil all globs up and floats to the top. All right, and even if I stir it up really, really good, the oil, we can see the little oil drops, it's all start sticking together, and they're all going to start floating to the top again. And if you've ever made pasta, you've probably seen the same thing. I remember as a kid seeing, my grandmother taught me you put olive oil, it keeps them from sticking, and it makes the noodles taste better when you're cooking pasta. But I would stir that thing up, and the oil would all glob back together, and then go back to the surface. And it says, why they thoroughly mix them, and it goes, why won't they mix with each other? All right, now it's not asking why does the oil float on top? The oil is less dense. We're not worried about that. What I'm concerned about, or what the question is asking, is why won't the oil and water mix together? If we poured sugar, if we poured salt in there, it would mix together very easily. Why doesn't the oil float together? Or why does the oil go together and won't mix with the water? All right, I'm not sponsored by Pepsi. I just happened to these to be on sale, so this is what I bought. You see 2 cans. This one over here, the silvery one, that's Diet Pepsi, and the one that's in the bottom here is the regular Pepsi. And I want you to notice what happens if I push the Diet Pepsi to the bottom. It comes floating back to the top, but that Pepsi, the regular Pepsi, is already stuck on the bottom. All right, so why is that? What's the big difference between the 2 types of Pepsis? Well, if we read the Diet Pepsi, what the ingredients are, it says it has carbonated water, caramel color, aspartame, that's a sweetener, phosphoric acid, and potassium benzoate. Has some caffeine, has citric acid, natural flavoring, and the rule is when you put things on a label, it has to be the same. It has to be in order of what there is most of. So there's mostly water, there's mostly caramel coloring, and the third thing is aspartame, which is a sweetener. Now let's look at the regular Pepsi. The regular Pepsi list says carbonated water, that's the same. And then the next one says high fructose corn syrup. High fructose corn syrup, that means that's water. I mean, that's a really sweet sugar, fructose, that's dissolved in water. That's what makes it corn syrup. And so there's a lot of sugar in this. Matter of fact, I think that there is usually most pop has between 12 and 16 teaspoons of sugar dissolved in it. Caramel color is on here. The other one had caramel color. This one says more sugar, has phosphoric acid. That was in there. Caffeine, citric acid. It's pretty much the same things, except for the 2 things that I mentioned in here, the high fructose corn syrup and the sugar that's added to this. All right, so go ahead and answer the questions based on that.